This is a tNavigator training course. We show how to split the model into arbitrary fragments, how to take advantage of multiple interactive restarts of parallel calculations, and how to add Weld patterns and simulate hydraulic fractures using new generation of adaptive multipoint flux approximation and full permeability tensor. This is the model loaded in Eclipse 100 format. Let's go ahead and define the borders of the fragment which we would like to cut out from this grid. To do that, we position the model, select the profile manager, and start clicking on grid blocks which define the border. Almost done and finished. Press OK. Now we need to create a filter out of this region. We edit map, reset all the blocks to 1, and define the fragment which we'd like to cut out. Close. To invoke splitting procedure, we go to the splitting manager, specify the filter, cut, and press OK. The splitting procedure is fully automatic, and it goes around the blocks, wells, regions of PVT, skull, and so on, and divide them between newly created fragments of the model. The split is finished. Let's load the newly created fragment. Okay. The newly created model is self-sufficient, also in Eclipse format, and identical in shape to the region we specified in the large model. Okay, let's do some work with the newly created fragment. To begin with, I'd like to add 5-spot Weld pattern. I invoke the manager of Weld patterns, press setup, and create 5 by 5 spot with injector in the middle and 4 producers in the corners. Also, I'd like to rotate it by 135 degrees with respect to x-axis. Press OK. And now I need to find a good spot to put this pattern. We point the cursor to the place where we'd like to have the middle, the center of the block. Have a Control pressed and then left button of the mouse. All wells are introduced, and let's press the execution button. Let's run the simulations. As you can see, this is a parallel simulations, so all 4 cores of this computer are fully loaded. We can go now to graphs and check out the performance of this pattern. You can see the integrated oil rate in red and water rate in blue shown for the newly created pattern. Also, we can see the production rates of the individual wells. Let's go back. And now let's rearrange the windows and get some new graphical window for the introduction of new horizontal well. Let's check out the production in 2D with streamlines and bubble map visualized. You can see this pattern is working. Now let's create a vertical profile for our horizontal well. We invoke again the profile manager and specify the line connecting the blocks we'd like to have in a profile. Alright. Switch to profile and zoom in. Now let's go to user maps and get the map of the resource and surface conditions. Let's do our first interactive restarts by sliding back the to the step number 10. And let's introduce the horizontal well. We switch the wizard to single well, press Ctrl and left mouse click through all the grid blocks where the trajectory is supposed to be. Right, we are done. Now press the run. See this well starting to produce. You see the streamlines. And let's get additional graphical windows to get the full view of this new horizontal well. Now we got all the windows arranged. This is the rates of the perforations of the newly created horizontal well. This is the list of perforations. This oil rates in red and water rate in blue. This is the total rate of all the connections together, so a combined rate of the well. And this is the distribution of the 3 lines in 3D. This is in 2D. Let's wait till the run is finished, do a restart, and actually simulate the fracture using full permeability tensor. Let's restart the run. Let's go back to this time step, let's say 12, and restart. We pause the run and define the permeability tensor here. We made a highly distorted permeability tensor with a 2000 millidarcies along y-axis rotated at 135 degrees. It corresponds to the direction towards the closest injection well, like shown in this picture. We press OK and specify the grid blocks where we'd like to make this fracture. We press Ctrl and click through the grid blocks and press run. What we see on the screen, that picture changed dramatically. It's actually a unique feature of tNavigator. According to the displayed streamlines distribution, we can call it a diagonal flux. It's a new advanced technology invented by Rockflow Dynamics and implemented in tNavigator. It allows almost complete removal of all the orientational effects of the grid, even when the grid becomes orthogonal or nearly orthogonal. None of the existing simulators can do this. The widely used 27-point flux approximation actually breaks down in the case of orthogonal grids. The new flux approximation is adaptive and only applied for the specified blocks. Effectively, with this approximation, the grid block becomes a PEBI grid with equal connectivity between the block and all its neighbors. Because the fracture points towards the injection well, we can see much higher rate of water and a little bit less of oil rate. Let's restart the run and change the direction of the fracture. Alright. To do that, we invoke Fracture Manager and change from 135 to 45 degrees. Okay. The new fracture direction now points away from the injection well, and we expect much less water rate. We can see the dynamics of the streamlines distributions, and also the production rates of the well change dramatically. We can see much less water produced and approximately the same amount of oil. To summarize, I'd like to say that we showed multiple interactive restarts, capability of user to add well patterns at the runtime, to add horizontal wells, simulate directions of hydraulic fractures also at the runtime interactively, and all of this can be done only with the help of tNavigator. This concludes this chapter. Thank you very much.